The DC-DC converters, or in particular the buck converter, or also known as the step-down converter. So let's make a simple intro to DC-DC converters. So DC-DC converters can be used in like different applications and different purposes, but the input is DC and the output is DC, so we can use them to either step down the voltage. They are called the step down converters or buck converters, or sometimes we may need a higher voltage than our input voltage. So in that case we can use DC-DC converters to step up the input voltage. Those are called the boost converters, so they can increase the output voltage with respect to input voltage. Or there are also converters that can make both of those purposes. They are in general called buck boost converters. So let's first start with a simple step down converter. Okay, assume that you need to design a DC-DC converter where the input voltage is 100 volts and the output voltage required to be 50 volts. So what kind of circuit can we use in between? Maybe the first idea that comes to your mind is just to use a resistance. So if we can just connect a 5 ohm resistance like that, so we can have the sort of 50 volts output. So if they are equal, and actually if we can just connect the resistor here, maybe we can change the magnitude of that resistance and we can control that output voltage. Again, that is acceptable for signals and that kind of analog voltages, but if you are talking about some power applications, for example, we are talking about 10 amps here, so the power loss will be equal to output loss and the efficiency will be like 50%, so it is not acceptable for any kind of power electronics. And maybe you can also propose to use a BJT in like linear mode, and you can have that kind of linear regulator, and you can control the gate or base current to adjust the 50 volts across the terminals of the transistors. And actually these are how like linear regulators work, like LM7805s, LM7812, something like that. So those are those are called the linear regulators, and basically they dissipate rest of the voltage. So if you want to get a 50 volts from 100 volts input, again they are like 50% efficient, and it's not acceptable. And if you actually get your phone charger, laptop charger, or power supplies of your laptops, they need to be like as efficient as possible, and for that purposes we generally try to avoid using like lossy elements. For that one, resistors shouldn't be used in series to regulate the voltage because they dissipate heat. And it's the similar for the linear mode BJTs or similar transistors. What we can use, as we will see in the following slides, is we can use capacitor to regulate the voltage. We can use transformers, magnetics, or like normal inductors again to store energy. Like capacitor is the energy storage element, as 1 over C V square is the amount of energy stored in a capacitor. And you can use inductors as well as a storage element, and they have an energy of like 1 over I square L, so they can also be used to store energy. And instead of like transistors working in the linear mode, we will use like MOSFETs, IGBTs, that kind of things. Again, we are not getting into details of those switches in this course. You can just assume we use the ideal on-off switch. Okay, either our transistor will conduct or it will isolate its terminals. Okay, so let's move on. And if you would like to use that kind of switch, maybe what you can propose is to use a switching power supply, as we will see. So let's have a look at some practical converters. So again here, DC-DC converters are used in all different purposes of DC-DC conversion. So you can have either smaller voltage or higher voltage at the output. And I will just show you a couple of slides, and I would like to show you like common circuit elements. So here, of course, you see the capacitors, and this is capacitor, and this is inductor, for example. As far as I see, probably that's a diode. It says D2, so that is a diode. Probably that one is a switch, or it is a transistor. And they have like some kind of controller, as I said in the previous week's video, so you need some kind of feedback mechanism to get some constant output voltage. And again, if you look at the here, again you have capacitors here at the input and also at the output. There's a fuse, and that toroid one is that, again, that is like inductor, and the I don't know which one is which one. Let's say that one is either diode, and here it's like MOSFET, and they are connected to some heat sinks to dissipate heat, because you know they are, at the end of the day, they are not ideal components, and they dissipate heat with respect to conduction and switching. But again, you have all those purposes here. This is a different DC-DC converter. Again, this is like the capacitor, and this is inductor. I don't know what topology it is. It has two inductors, and again this is capacitor, and probably I don't know either that one or this can be a diode. I'm not sure. There's another switch here, and then here's the controller. Okay, and there's again small kind of adjustable resistance to control the output resistance, but again this is not the main path. It is not like a resistance division. Okay, so the main current is only carried through the inductances, capacitances, diodes and switches. So we will get into those components. Let's start with the simple, very simple buck converter that you can make. So for example, let's say you have like 12 volts at the input and you want to get like 6 volts at the output. What you can do is you can turn this one on and off, okay, for 50% of time. So duty cycle, let me define those things first. So duty cycle, let's say D is 0.5 in this case. So duty cycle is T on, okay, on time divided by total period, okay, or in other words you can write like T on period is equal to D times TS. We will talk about that one. So anyway, so you just turn on like 50% of the time, depending on maybe 1000 times a second. Let's say your switching frequency is 1 kHz, so you are doing that thing like half millisecond on and off. But at the end of the day, what kind of output voltage that you will see is like that. Again, probably this is not the 50% case, whatever, but here whenever the switch is on you have like 12 volt, and whenever it is off you have just the resistance and you have 0 volts. Okay, so that is our input voltage. So T on, okay, T on again is equal to D time TS, and T off is equal, let's say, 1 minus D time TS. Okay, so all period is like TS, and duty cycle defines what is the percentage of your on time. So D is between 1 and 0. So either I can like turn on it all the time with a duty cycle of 1, so I will have 12 volts at the output, or I can have like no I can close switch always, so it is like the duty cycle is 0, so I will have 0 volts. Okay, but the problem, as you can see, okay, whenever the switch is on you see the input voltage, whenever the switch is off you see 0 volts. So it is not a constant DC voltage, but it is like a square waveform, so it is not really ideal. So what you can do, okay, let me try to plot that circuit. So at first we have, let me draw it smaller here. Okay, so here that is our switch. Again, this is not a mechanical switch, think it like a transistor, but I just plot it like a switch. So you have your input voltage, you have your output voltage, and this is just resistance. So maybe the first thing that you can think is like, let's connect a capacitor, right? So that is really good, and you can connect the capacitor, and capacitor will store some energy. Again, that can be acceptable for some current ratings. But what will happen, okay, what will happen if you just use a capacitor? If you close the switch, and initially at the initial condition, if that output voltage, let's say if VC is 0, so you have V in like 12 volts and capacitor is 0, and you will have like here like large inrush current. If you just use a capacitor like that with a switch, when you first close the switch, there will be lots of current trying to charge the capacitor. And again, this is not a mechanical switch, this is a MOSFET or that kind of transistor, and you can damage your transistor. So again, we need to limit that current. Maybe you can say let's put a resistance, but again we want to avoid the lossy components. So what we can do is we can add a so secondly, what we can do is we can add the inductor, right? So V in, and now we have our resistance, this is our V out, and we have our C, and we have our L. So now, when I close the switch, so the current cannot increase instantly, so inrush current is limited. Let me write it like that one. So here, inrush current is limited. But now you have another problem. So if that inductor current is conducting, and once you close or once you turn off your switch, let me use it like orange. If you turn off the switch, so once the switch is turned off, so the VL is equal L di over dt, and so VL, again assuming this is an ideal switch, VL goes to minus infinity when the switch is off. So again we have some problem. Again, once we have some inductor current, current, and you can't make that thing 0 immediately. That was a problem also in electric machines. So because if you want to cut off that current 0 immediately, that will give you infinite amount of voltage. Now you will destroy your MOSFET, not because of overcurrent, but you will destroy your MOSFET because of over voltages. So we need to have some path for that inductor current. So that gives us to that classical buck converter topology. If we can just add here a diode, and this is diode, this is switch. So once you close that switch, the inrush current is limited, and once you turned off that switch, so now the current can flow through that path. So that is that topology. Again, don't worry, we will see the details of operating modes. So that topology is called buck converter. So I just wanted to to define the purpose of each component. So that is a classical buck converter. So we have the LC, so you can think LC like a low pass filter, so it gets the high frequency PWM signal, and you can get a nice output voltage here. here, and actually there's an online simulation tool that you can play with, so you can click on that link in the course slides, and we put the diode, okay, we put the diode to have a path when the switch is off, so the inductor current can be continuous always. So it is called the freewheeling diode, and it conducts when the switch is off. Okay, so that is the topology for the buck converter. So let's try to analyze that converter. So there are basically two operating modes for this buck converter. So let's try to see what happens. So when the switch is on, okay, switch is on, okay, so you will have current flowing through here, okay. So when the switch is on, your supply charges the capacitor and the load. Through inductor. Okay, so you are closing that switch and your voltage is trying to increase the voltage here, and again I'm talking about like thousands of times switching here. We are talking about like really small time steps. Okay, so and next one, let's use the green one. So you will have that path. So in that one the switch, okay, switch is off, and whenever the switch is off, your V in is disconnected. So you have no connection here now. So then L1 discharges through C and R or LR. Okay, so these are two operating modes, and depending on how long you turn it on and how long you turn it off, you can control the output voltage. Let's try to calculate, and let's try to plot the output and output voltage and current waveform. So let's look at the first state, and let's call that one V in, and let's call this is like V out. Okay, and there are some assumptions that we will do, and I will show those assumptions in the next slide, but just to summarize, we assume, again, if you look at that thing, it's the LC circuit, it's the second order system, it charges exponentially and that kind of waveforms, but we assume that our first, we are working at the steady state conditions. Steady state conditions means we are not immediately turning it on. Again, we will cover those things in the 4th year power electronics course. And secondly, we assume capacitor is large, C is large enough, okay, so that V out is constant. Okay, so we will not taking into account now what is happening to the capacitor voltage in those small instances. So if we assume output voltage is constant, okay, and our input voltage is also constant, let me try to plot the inductor voltages and currents. Okay, so first let me plot the VL. So I'm talking about here VL, and let me try to draw inductor current as well. Okay, so whenever we have positive voltage here, so switch, let me put it here. So sorry, I didn't see, I blocked the writing. And let's say the switch is on, and for that one diode is off. Why? Because it is reverse biased and the current cannot flow in that direction, so we don't have that path, and the current just flows through here, right? So I'm just interested in IL. So for inductor, what is important is the voltage at this node and at this node. At first, so we have the input voltage, okay, so this is V in, so this is V out. So basically what we have here is, let me try to, this is VL, so I will have V in minus V out, right? V in minus V out voltage. And for how long? For my duty cycle, or in other words, for D time Ts. Remember, D time Ts is equal to T on. Ts is the total period. And what will happen? Okay, what will happen to my inductor current? Again, I'm not taking into account of what will happen if it starts from 0. Let's say I0 is equal, there's some current. So we are starting with some I mean steady state current. So what will happen is, for that time I know VL is equal L times di over dt, and VL is equal to V in minus V out is equal L times di over dt. And again, you know, in the real case, the output voltage is changing as it charges the capacitor. Yes, I know, but we assume that C is large enough so that output voltage stays constant. So if it is staying constant, then the inductor sees a, you know, constant voltage. So that means if this is constant divided by L, then IL charges linearly, right? So if you apply a constant voltage to an inductor, its current is going to climb up linearly, and it will start up somewhere here and it will come to that thing, and let's call this I max, right? So it just comes to here, right, during the on state. So now let's move to off state. So now in the off state, I just closed my switch. So switch is off, and then I had some inductor current from my previous case, and the diode starts conducting and L discharges. So let's try to plot those things. So let me try to draw the same graphs again, right? And let me put again the same things. Let's say this is VL and this is IL. So at first, let me use the line. So we had for some time we had our current, and during that one our inductor voltage was charged. So this is what we have here, right? So this was V in minus V out, it just charged here. So then, and this was for again D time Ts period, and then I have, let me write those things again. Output voltage is constant, and this is my VL, right? So what is my VL? So now VL is connected here, and this was 0 volts. So VL is here, VL is minus V out, right? So my inductor voltage just came down from V in ex V out minus V out, sorry, to, okay, which one, minus V out, okay. And for how long? For the rest of the period, right? So then it will come back here. So what will happen to our current? So our current will come back to some place. We will calculate that one, right? But now what we have here is VL is equal to minus V out, and I know VL is equal L times di over dt, and minus V out is equal L times di over dt, right? So it discharges linearly. I mean, you can still, write that thing as like IL, okay, t is equal to VL dt minus I0, right? So once you write it like that, you can see if you see a negative voltage and the derivative is like negative voltage, so our inductor current will discharge linearly. Let me plot it this better. Okay, so, and this period is how long? This is 1 minus d ts, and the whole period here is ts, right? So I have that kind of voltage and current characteristics. So how can I analyze the output voltage? How can I solve this circuit? And for that, I need to make some assumptions. Let's move to that one. So here you see the better graphs of what I just plot. You have the on and off states for the switch. So whenever you see the on, your output voltage, the diode voltage is V in minus V out, okay, and then your inductor charges linearly, and whenever like it is off, your inductor voltage is discharging linearly, right? Okay, so that voltage, let me rewrite those things. So that is V in minus V out, and that voltage here is minus V out, and this is VL, right? Inductor voltage. And here you are starting from some current and you are increasing linearly, and then you are decreasing and you are getting back. So now the assumptions that we are going to make is, first we assume the converter is working under steady state. So under steady state means, so we have our period here, okay, so this is our switching period. So I just start with I min current here, and I climb up and I came back to the same position. So I mean, again, this converter will have different characteristics if the load has suddenly changed, or if you just turn on the converter, that kind of things. But for now, as an introduction, we just assume it is working at steady state, and steady state means I0, or let me write not IL, 0 is equal IL T. Okay, so that waveform just repeats itself. And the next thing I assume is capacitor is large, so that output voltage is constant. So V out is constant. Again, if you want to really calculate the output voltage waveforms, it is a second order differential equations that you need to solve. It's an LC circuit, and you can still do that using computer simulations, but for now we assume the C is large. And again, we are talking about like really high frequencies. Maybe you are switching it like 10,000 times a second, those MOSFETs, and the voltage ripples in the capacitors will be small. So what can I say about that one? So that one is steady state characteristics. So that is really important for me. So I can write, for example, forget everything and just look at that inductor, right? I can write that inductor voltage like that. So let me rewrite it here. So you can write IL T is equal to integral of VL, okay, T dt 0 to period plus IL at 0 initial condition. Integral of voltage gives you the inductor current at T. Okay, so let me write it T, or let me rewrite it like capital T here. Okay, cool. So then, that means if you are just applying some positive voltage, so it will end up increasing its current, with respect to its initial current. Or if you apply negative voltage here, it will end up getting a lower current. That's what you expect from the inductor. And if it is working at steady state, so from here to here, right, it is under steady state conditions. So that means ILT is equal to IL0. So actually I can bring it to here. ILT minus IL0 is equal 0 to T VL T dt. And if I know these things are equal to each other, the difference will be 0, right? 0 will be equal to 0 to Ts or T VL T dt. So in other words, okay, in order to operate under steady state conditions, the total inductor's voltage should be equal to 0. That is probably the same thing that you expect from a capacitor. Again, not only for this capacitor. So if you have a capacitor here, right? So if you are having some capacitor voltage, and if that capacitor voltage is constant at some time later, that means the amount of charge getting into that capacitor and the amount of charge, okay, I in, let's say I out. So if you integrate I in with respect to time, which gives you the charge in columns, and if you integrate I out with respect to time, it will give you the amount of charge out. So if the out capacitor voltage is not changing, that means the capacitor or the charge will be equal to 0. That is the same thing for inductor. If the current of an inductor is not changing, so it starts at I min and it finished at I min, so that means during that time, that area, okay, let me show it with red. So that area, the red area and the blue area should be equal to each other. They should cancel each other. If they don't cancel each other, that means there's either an increase or there's either a reduction in our voltage. So I will use that property to calculate our step down converters characteristics. So let me show it here. So here we start with some current and we end up with some current, and again these are the same thing with the previous graphs. I have A and I have B. A should be equal to B. Okay, the voltage, this is called voltage seconds balance for an inductor. Okay, so let's try to calculate those areas. So the first one, remember, it was V in minus V out, and the other one was minus V out. So these two areas should be equal to each other. So the first one, V in minus V out, and I want to calculate that, red area, or in other words, I'm basically doing like 0 to T VL dt, that is equal to 0, right? So the first one is here, and for how long? For d time ts, and again here I'm talking about the absolute values, or you can just use the real values to add those things. So the second area, it is minus V out, okay, times 1 minus d ts. That should be equal to, that should be equal to 0. Okay, so you can get rid of ts. So you have V in times d minus V out times d minus V out and plus V out times d, that is equal to 0, and you can basically see that one and that one cancels each other, and you have a really simple equation, which probably you already expect. V out is equal to V in times d. Okay, so output voltage is equal to input voltage times duty cycle. So if you apply a like 50% duty cycle, you obtain half of your input voltage. If you apply, let's say, if your input voltage is 12 volts, let me get rid of myself, okay, if D is 0.5, then your output voltage is equal to 6 volts, okay. So if V in is equal to 12 volts, and if you just use a 0.25 duty cycle, then your output voltage V out should be like 0.25 times 12, it will be 3 volts. So by changing, okay, so by changing the duty cycle, you can control your output voltage, from 0 to input voltage, and that is a buck converter. Okay, so now I have the relation between output voltage and input voltage. You can think like this: input voltage, and ignoring all losses. Again, we don't have any lossy elements in our DC-DC converter. Let's say this is buck converter, okay, and you have your output voltage here, and then you have your current here. Of course, you connect some load there, right? So you can have your V input voltage, and you can have some input current. So let's say your output voltage is like 6 volts, and your output current is 2 amps, right? So, and if V in is equal like 12 volts, so duty cycle will be 0.5, and from output, I mean, you can convert like a resistive load, whatever it is. So you can connect a resistive load that draws 2 amps, so you are delivering 12 watts. And of course, in real life, we have the diodes conduction losses. The inductor has some resistive elements. The switch will have switching and conduction losses as well. But if we ignore all of those things, okay, so we are delivering like 12 watts, and the input, okay, should be, again, will be 12 watts. So the thing I would like to emphasize is, yes, we are reducing voltage, but we are increasing current, okay, in order to have that thing. And actually you can drive it using the current equations, like the voltage equations that we use. So what you can represent, neglecting the losses, you have output voltage is equal to, again, that call them like input output voltage is duty cycle D is, let me write it here, duty cycle, and D, as we discussed before, is between 0 and 1. So that means the current, okay, the current that you are drawing from input is IO is equal I in divided by D. So it is, in some way it is like a DC transformer with a turns ratio of D to 1. So we are reducing the voltage and we are increasing the current at the output. Okay, thank you.